K draws a 6x6 grid. He colors 13 of the unit squares silver, and the remaining squares gold. K then folds the grid in half vertically, forming pairs of overlapping unit squares. Let M and M, in lowercase and uppercase, equal the least and greatest possible number of gold-on-gold pairs, respectively. What is the value of M plus M? So first we want to figure out how many gold squares K colors. So we're given that 13 squares are silver, the remaining are gold. The total number of squares is 36, since that is 6 times 6. So when we subtract 13, we see that 23 of the unit squares are going to be gold. So let's first maximize the number of gold-on-gold pairs. This happens when we have as many corresponding pairs as possible, meaning that for every gold square, there is the opposite square is also colored gold. So we want to maximize the number of these types of pairs. And we can see that we can achieve 11 pairs, because 23 divided by 2 is 11 with remainder 1. And so one way of doing that is to simply color these squares gold. We have one more, but that's not going to make a pair. So this proves that 11 is the maximum number of gold-on-gold pairs. So we will write this down. Now, to minimize the number of gold-on-gold pairs, we're going to want to do the opposite, meaning that we want the gold squares to intersect the fewest number of times. And so one way we can do this is to actually color the entire left half of the grid gold. This leaves only 5 squares left to color gold on the right-hand side. And so this will imply that the minimum number is 5. Now, this is not a completely rigorous solution because this only shows that 5 pairs is possible, but it's not too hard to show that if we only have 4 pairs of gold on gold, then we cannot possibly color 23 squares gold in this way. So given this, we conclude that the desired value is going to be 5 plus 11, which is 16, or choice C.